Okay. Thank you very much for the invitation. Is this as big as it gets? This is maximized? I guess it's fine. Right, everyone can see. Okay. Yeah, that's what I was wondering.
Yeah, those. Maybe let's see. No.
Okay, it's fine. Yeah, so I'm going to tell you a little bit about some work in progress with Kimoy Kemboy and Špenko on well, equivariant derived categories of coherent sheaves, but I'd like to tell you a little bit about the background and how I got here and how it's related to other things that I've spoken about actually at this conference last year and before, namely the noncommutative minimal model program. So the motivation for this subject, and actually, somehow motivation for lots of very interesting developments in algebraic geometry over the last few decades, is this Bondel-Orlov observation that, at least for these kind of simple flops where you can say explicitly locally what's happening, they construct a kernel giving a derived equivalence between one variety and its flop. And similarly for simple flips, that tends to shrink the derived category as you move closer to the canonical model, I should say. The derived category gets smaller and smaller. So this is raises some general questions, which I think was posed by Bondel-Orlov, eventually became known as the D-equivalence conjecture, which is basically anytime you have a birational equivalence like this that preserves the canonical bundle, at least for projective manifolds, you'd expect there to be an equivalence of their derived categories. And there's also a local version, which is similar, but basically, x and y, x and x prime will sort of live over some affine base like this, and then you want the equivalence to be linear over the coordinate ring of the base. So this is the kind of motivational problem. I'm not sure if this historically, if this came first or shortly after, but there's a reasoning for this, an explanation, at least in the projective Calabi-Yau case from homological mirror symmetry, which is part of the yoga of mirror symmetry, is that complex deformations on one side correspond to Kähler deformations on the other side. And if you think of a flop as a kind of Kähler deformation, then the mirrors should be complex deformation equivalent, and so they'll have equivalent Fukaya categories. So that if you believe homological mirror symmetry and all these pieces of this philosophy, then you get that the birationally equivalent Calabi-Yaus have equivalent derived categories. So that's an explanation, but it's not really a strategy of proof, because the mirror constructions is not, the current technology, we don't have very, very general mirror constructions. So there's not even a way to make this kind of perspective work in general. So algebraic geometers have worked hard. Many people have kind of thought about this and have approached this conjecture in special cases from different perspectives. So it's kind of interesting. So the kind of, the best possible answer, in some sense, is if you could just write down a kernel for a Fourier-Mukai transform. So that would be a complex on the product, and you pull back, tensor with the complex, and push forward. And kind of Bridgeland did this in 2000 for Calabi-Yau threefolds. It's kind of miraculous that in that case, the flop x prime has a description as a moduli space of certain complexes on X, and the kernel is just the universal object on X times this moduli space. The universal complex turns out to give you a Fourier-Mukai equivalence. And then that's basically it for explicit kernels, except recently, the Malik, Shen, Yin, and Zhang proved the D-equivalence conjecture for projective hyperkählers of K3n type, basically by showing the existence of a certain explicit kernel. I mean, I guess it's not really explicit. They start with some hyperholomorphic vector bundle, and then they show that you can deform it to some kernel that becomes a derived equivalence. means that it's deformation equivalent to a Hilbert scheme of points on a K3 surface. But I mean, most compact hypercalars are of K3n type. So yeah, the exception, the O'Grady ones, yeah, but most of them, yeah. So this is pretty cool. But probably the threefold case and the hypercalar case are kind of very special. And in general, I'm not sure if you can hope to construct super explicit kernels to prove this conjecture. So there's another kind of perspective, which is this noncommutative resolutions. I think this is pioneered by van den Bergh shortly after Bridgeland's thing. And in the local case, so that's when you have it's a little bit more general, but basically an isolated Gorenstein threefold singularity, spec of R, and you have this resolution by a Calabi-Yau threefold, a Crepin resolution, then you can construct a tilting generator. And basically, there's a third object which interpolates between the derived category of X and the derived category of its flop, which is a different resolution of the same spec of R. And basically, what that is a category of modules over some noncommutative algebra. And van den Bergh calls this a noncommutative, in this case, Crepin resolution. And then so, as mathematicians, we're not just looking to prove that something is true to know that it's true. We're trying to understand why it's true. So I would say the explicit kernel thing is kind of a miracle. This noncommutative Crepin resolution is saying, well, maybe this is true because there's some kind of generator, and its algebra of endomorphisms itself is a birational invariant, which is basically what's going on here. That if you take on one model and the other model, those two reflexive sheaves agree on a set whose complement has high codimension, and so the algebras of endomorphisms are literally the same. And because it's a tilting generator, you get derived equivalences with the same algebra. This approach, again, is something that seems to be maybe specific for threefolds and hypercalars. Bezrikhovnikov and Kaledin proved a similar approach. I mean, kind of motivated by questions in representation theory, but they studied these symplectic resolutions, which is kind of the local version of a hypercalar. And specifically, they were very interested in this one, where you take C to the 2n, mod the symmetric group, and Hilbert. And basically, they get a derived equivalence between those two things for the same reason, that they find a tilting vector bundle that generates. And so you get this non-commutative algebra that interpolates. So those are two approaches. And then the third is the one that I've worked the most on. So basically the situation, I'm going to assume X is smooth for most of the talk, but that's not, sometimes it works when X is singular. But the situation is that you have an X that has a good quotient. This is a technical term. So you can think of X here would be either an affine variety, and G is a reductive group. Or X could be the semi-stable locus for some GIT problem. So I'm not including that in the notation, because what I want to do is, if you have a variety with a G action that has one of these good quotients, then basically for any line bundle or any class in the equivariant Nernst-Savary group, you can define a notion of semi-stability with the Hilbert-Mumford criterion. Wait, maybe I have. Okay. Yeah, so you could define a semi-stable locus basically using the Hilbert-Mumford criterion, and that will also have a good quotient. So the picture that you should have in your head is that you have some stack, and that kind of, you have a stack up here, X mod G, whose good moduli space is that, and then you have these open substacks. So semi-stable locus for some class L, and then semi-stable locus for some class minus L. And they also have these good quotients, and you have a picture like this. So this is what, like a variation of it. It's an intrinsic way of thinking about a variation of GIT quotient. And in this case, the Calabi-Yau condition. So I should say that you can study many birational transformations this way, but the ones that you expect to give you derived equivalences satisfy this Calabi-Yau condition, namely that the canonical bundle of the variety is equivariantly trivial. And so this variation of GIT approach basically identifies a subcategory. Oopsies. Yeah, so. Yeah, so. Okay, so I get this subcategory that I call G inside the equivariant category. And just like in the last picture, there's this kind of third non-commutative object that interpolates between X and X prime. In this picture, that role is played by a subcategory of the equivariant derived category. And this is a template. And I guess I only go from L to minus L because it just kind of simplifies things. In general, what you sort of do is you want to go from L and you perturb in one direction, or L and you perturb in the opposite direction. But that's secretly just exactly the same thing. You just replace your original X with the semi-stable locus for L, and then it's exactly this situation. So in some sense, every wall crossing, looks like semi-stable locus for L goes to semi-stable locus for minus L. So yeah, and so I've assumed X is smooth, but you can get a lot more interesting categories if you work with matrix factorizations and singularities. So everything I'm going to say also works for those categories, but for simplicity, I'm not going to emphasize that. And so this approach, this concept of having an equivariant category, a subcategory of the equivariant category interpolate between GIT quotients goes to Horry, Herbst, and Page. And they were studying this in the context of the gauge linear sigma model, identifying these kind of special branes that they could transport from one limit to another limit. And then Ed Siegel wrote this paper explaining in more mathematical terms, in a way that I could understand, this specific example of a linear representation of C star. So it's very simple and very beautiful. You can do everything very explicitly. And so then shortly after Ed wrote his paper, myself and Ballard-Favero-Katzarkov actually generalized this to arbitrary wall crossings of the kind that I'm talking about. When I say this, I don't mean the equivalence. When I say this, I mean the theorem that identifies the category G. And that's actually going to be kind of the thing that I'm going to be focusing on today, is that there are these very general theorems to identify the category G, but you don't always get equivalences with both sides. So this project that this new stuff that I'm talking about is how to get better categories G that allow you to more easily compare two different quotients. So that's going to be the theme of the talk. But at least identifying some category G in the equivariant category that's identified with the GIT quotient was handled in general in these two papers. And what I sort of said in words is basically the only time you can identify the G category for one GIT quotient with the G category for the other originally was for these very simple wall crossings, which essentially locally look like a variation of GIT quotient of C to the n by C star. So it's a very basically reducing to the model locally to this Ed Siegel calculation. So the next thing that happened was that we discovered a class of examples that are not so simple wall crossings, the kind of thing that happened when you're studying flops of Nakajima quiver varieties that are not simple, and you can still find a G category that kind of magically is identified with both GIT quotients in that case. And then I kind of generalized this further to the zero-shifted symplectic stacks, or stacks that have a self-dual cotangent complex. Yeah, any reflection really. It's basically there's a category. Yeah, so in this quasi-symmetric case, I'll explain what that means a little later. But in the quasi-symmetric case, you can identify a subcategory of the equivariant category that just is equivalent to any GIT quotient under restriction. And that's like, Yeah, that's called these magic window categories because I can't see any reason why that should be the case, that you should find some single category that's just simultaneously equivalent to all GIT quotients under restriction. But in this quasi-symmetric situation, that's what happens. So this does a lot of things like these hyperkähler quotients and so forth, but it leaves a lot unanswered. Namely, the original prediction is that under the CY Calabi-Yau condition, all of the GIT quotients should be derived equivalent. So yeah, so basically what I'm going to talk about today is a new approach towards the general Calabi-Yau case. And I'm going to discuss a little bit how these previous approaches that I discussed are related to one another, except for the explicit kernel one. That one I have no idea about. But this idea of that there's a close relationship, it turns out, between noncommutative resolutions and these window categories. And so I'm going to be discussing that as well. So this is a bit of a terminology because people come up to me sometimes and be like, oh yeah, like I like window categories. And it's a sort of informal term, but I'd like to actually break it into two more precise terms. So if you have a quotient stack like this, I want to say that a window category is some category that's generated by vector bundles of this form, where it's given by explicit generators, where you just take the structure sheaf, you tensor with the representation, a highest weight representation, let's say, for highest weights in some convex set. On the other hand, another category that plays a role is the so-called grade restricted and complexes, category of complexes that satisfy grade restriction rule. And these are local constraints on the weights. And yeah, so the original approach actually produced these kinds of things. So it produced these categories where you say, if you consider the subcategory of complexes that satisfy some local constraints on the weights at various fixed points, that subcategory of complexes is equivalent to the GIT quotient, but it doesn't provide generators for that category. On the other hand, you can, as Alex was saying, you can try to define category by some generators, but then it isn't always equivalent to the GIT quotient. And these categories G are very explicitly not always generated by vector bundles, because if they were, then every toric variety would have a full exceptional collection of line bundles, and that, as mentioned, that's not the case. So that we know that there's some kind of gap. You can write down these sort of combinatorially described categories by saying they're generated by highest weight representations of this kind, or you can have these G categories, but there's some kind of gap, and that's what this new project is addressing. So actually, there's sort of an interesting thing that happened. So the original approach makes use of a canonical stratification of the unstable locus. It's like one of my favorite things, or at least, yeah, seems to be if you look at my work. But basically, there's this stratification, and every stratum has associated to it a canonical co-character, really up to conjugation. And if you take this data as just given, then the original grade restriction rules look kind of like this, which is you take a complex and you take its derived restriction to the fixed locus of SI with respect to this co-character lambda I. And then, that fixed locus was, because it's fixed by lambda I, every complex decomposes as weights under the action of lambda I, and you just require that the weights, which is this thing is non-zero, lie in some interval like of this kind. And you can just specify that shift parameter theta, you can shift these intervals arbitrarily, and the theorem still just applies. So you have these categories G, and it's equivalent to the restriction gives an equivalence between these categories, the category of complexes satisfying these conditions, and the semi-stable locus. And the proof is just inductive using this stratum. You can basically reduce it to one stratum at a time, because you throw a closed stratum, and then you take the next one, you take the next one, and this condition is somehow, it's preserved. So the proof of this is really just a statement about a single stratum. And for simple wall crossings, it's easy to compare. So I didn't explain what I meant by a simple wall crossing, but here, what I mean by simple, I can make more precise, is that you have X, and then for one semi-stable locus, you have a single unstable stratum, and you have on the other, for minus L, you have a different unstable stratum, and then lambda, the co-character for one is opposite of the co-character for the other, and the two fixed loci are the same. This is what you might call a simple wall crossing. And in this case, you see that this condition is actually the same, literally the same, if the weights, so this is saying the restriction to this fixed locus, which is the same by hypothesis, has lambda weights in some interval. And as long as that a to I is the same on one side and the other, then this condition, this grade restriction rule is literally identical on both sides. And that's why you kind of, just kind of coincidentally, because it's so simple, you get an equivalence. You apply the theorem on one side, and you get an equivalence with one quotient. You observe that the G is actually the same description on the other side, and you restrict and get an equivalence. But in, and actually for abelian groups, this was also mentioned by Alex, if your G is a torus, then generic wall crossings are of this kind. And so this is enough to get you, in the Calabi-Yau case, say with a torus action, equivalences between all the GIT quotients. But in a lot of for non-abelian groups, there's much more interesting stuff that goes on. So the generic wall crossings are not of this kind. So the problem with this theorem, so it doesn't show up in this for these simple wall crossings, but the basic problem is that these co-characters, in some sense, they depend continuously on your choice of GIT parameter. And also the theta I, the parameters, the shift parameters theta I here are kind of arbitrary. And so what ends up happening is that even though the semi-stable locus is not changing, the subcategory G is legitimately changing as you vary your L. There's just not the same subcategory. And as you can imagine, that makes it really hard to say that the category for one GIT quotient is equal to the category for the other GIT quotient, because there's not even a well-defined category for the GIT quotient. It really depends on the L. But somehow it shouldn't, right? You should have a subcategory of the equivariant category that depends on just the GIT chamber, and that gives you a better hope of comparing them. That's the goal. The goal is that or the thing I'm going to tell you about is what I think is a better structure. It's a similar structure, but it's a more symmetric version of this theorem. And the subcategories that you produce have the same kind of semi-continuity, namely that the semi-stable locus is constant on L in some chamber of some fan, the variation of GIT fan. So that's So the place that I started is a kind of axiomatic approach. Instead of saying specifically I have all this structure on the unstable locus coming from the canonical stratification, I went to the other description of what the unstable locus is in GIT. That maybe is the simpler one for people in some sense. Namely, the unstable locus is the set that's the vanishing locus of all invariant sections of some G-equivariant line bundle. And actually, you don't have to, for what I'm going to say, you don't have to have, it just can be some set that's cut out by G-invariant sections of this line bundle L. So you fix this bad subset, this unstable locus, but it's described this way. And then the other bit of notation or concept that you need are these transfer functors. So basically for any co-character, it's just like before my lambda. Lambda always means a co-character. So for any co-character, this is the Levy subgroup associated to the co-character, and then there's a parabolic, and you have these kind of parabolic induction functors. I mean, generalizing the stuff that comes up in the Bergh-bot, right? So you take the fixed locus of lambda that's equivariant with respect to the Levy, the centralizer of lambda, and then you can pull back to this other thing. This is the subspace that has non-negative weights with respect to the co-character lambda, mod p lambda, and then you can push forward. And this map the map from this quotient stack to this stack is actually proper. So you can push forward and you get this transfer functor. Somehow these are the two key ingredients, is this S, the subset that you want to avoid, and the transfer functors. And that you can say, it turns out you can prove a theorem, and what's interesting is that the proof is non-trivial somehow, but still avoids all the messiness of actually studying the structure of the unstable locus. So suppose we're given a sequence of subcategories, CT, inside of this, then you sort of, sorry, this is, so then I'll define this category D to be just basically what I get when I take the union of all the CTs. Eventually, these CTs are kind of filtered, so some filtration of the category, and usually it's the whole derived category. And then you say the DSS is just the essential image of that under the restriction functor. So it's a subcategory by definition. It's a subcategory of the semi-stable locus, of the derived category of the semi-stable locus. So suppose we have this family of subcategories and they satisfy some axioms. So basically, you have inclusions. So there are finitely many real numbers where the category jumps. That's what this is saying. And then CT is a subcategory of CTI plus one. So basically, it's a semi-continuous family of categories depending on a real parameter, and it jumps in any finite interval. There are only finitely many jumps. That's the first thing, and then the second thing is that it should interact with the line bundle that you've chosen in the following way: that if you use tensor CT with L, that contains CT plus C, some uniform bound like that. And then you have this other condition that the category, this was the union of all the CTs, should be preserved by tensoring with L. And then you have this last condition, which is that basically if I want to understand the inclusion like this, basically, I want CTI plus one to be generated, first of all, by this CTI, and then the image under the transfer functor of certain complexes F. And what I want to say is that I want to be able to find lambdas that generate, these phi lambda of F that generate, so that there's some kind of bound where the lambda weights of F are less than or equal to W lambda, and the lambda weights of any object in the CTI are greater than W lambda. So what this is essentially an axiomatization of this of a very explicit algorithm that was designed, but that was the first version of it was studied by Špenko and Bergh. But actually, this is all you need, these axioms. So if you have a family of categories satisfying these axioms, then you get the following. So this is you should think of this as the template of a grade restriction rule theorem. So then the category D, which was usually the full equivariant derived category, has a three-term semiorthogonal decomposition where, so basically, U minus is defined as the semiorthogonal complement of the category CT. Yeah, and then this U plus is defined as the semiorthogonal complement of U minus in this DS. And then G is defined as whatever fits in the middle between those two pieces. So somehow all of the data of this theorem just comes from this filtration by subcategory CT. DS, what this really means is that these are the complexes that are supported on the unstable locus. And so that you get a decomposition of this stuff supported on the unstable locus into two pieces, a positive and a negative piece. And then if you take the whole category, you define whatever goes between those things as G, and that is automatically equivalent to the semi-stable part under restriction. So this is the sort of general theorem. of course, there's nothing polyhedral about what I've said. This is just something about some categorical stuff. So I'm going to narrow the focus a little bit. So the real place where this gets fun is when you just have like the GLSM situation, you have a linear representation X of a reductive group. And I'm going to, the Calabi-Yau condition, I'm going to assume that the determinant is trivial. And I'm imagining fixing a maximal torus, and I'm going to refer to the weight lattice as M. And the weights that appear in X I call those betas. And the key object that we're going to be studying is the zonotope. And this zonotope has come up a lot. I think I first heard the word zonotope in a talk by Paul Horja at some version of this kind of conference many, many years ago. And he was talking about how important the zonotope was for GIT. I think it's related to this Cox category is this zonotope. Anyway, and it's going to play an important role here. It also came up in the work of Špenko and van den Bergh. And the final bit of notation, and I apologize for notation, I'll try to keep reminding you what I mean, is that the inward, all I need to know are the inward normal co-characters of facets. And so basically I just keep track of this finite set of co-characters. And I just remember, I only need the anti-dominant ones. And this, I'll assume that sigma spans the weight lattice M. So then, now we're getting polyhedral. So I have this, I can define this polyhedron P. So I've drawn it for you. I can't even, this was from an actual example of a Calabi-Yau representation of a torus. But basically, you take this zonotope sigma, and you have some GIT parameter L, and you just take all the co-characters that pair negatively with L, and that cuts out a kind of polyhedron, the minimal polyhedron that kind of, it's the shadow of this zonotope with respect to those co-characters that pair negatively with L. And the idea is that this category CT, in our case where we're actually applying this theorem, is just a window category. Remember I said there are window category and grade restriction categories? So the window categories are very easy to specify. You just say, what are the generators? And so the window category here, I just say, okay, well, I just take OX, these tautological vector bundles for highest weights that are in this, I introduce a shift parameter theta, which lives in the same space as L. Basically, it's the category generated by highest weights that lie in a shift of this polyhedron P.
Just to make sure that in the picture, the L is not parallel to the...
No, L...
It's like more vertical.
Yeah, right. So it should be, thank you. Yeah, that's, yeah. There's a version when L is parallel, but it's, this thing the way I've drawn it here. Yeah, so actually if L is parallel to a side, then you get this. And instead of getting a decomposition of the whole category, you get a decomposition of that strip of the category generated by vector bundles lie in that strip. Oops, okay, that's not how to do it here. Okay, so, and I've just given a visual illustration of what makes this, remember the category should have some axioms, and it was the last one that was the most subtle, basically that the window category for a slightly larger, if I take a slightly larger one of these polyhedra, the window category should be generated by the small shift of the polyhedron along with some weights. I guess I've drawn it literally right here, along with some objects. And what you basically do is for each of these faces, you take all the lattice points, and I take the phi lambda, where this is my lambda, I take phi lambda of OX lambda equals 0 twisted by mu. So basically there are specific objects that I associate to the lattice points that lie on the boundary of some translation of this polyhedron. And those objects, along with the window category for small shift, generate the original window category. And that actually is all you have to prove. And then all of a sudden, that theorem that I just showed you that is takes effect and proves this thing. So it's kind of a modified Špenko-van den Bergh algorithm. So Špenko-van den Bergh had this thing where they studied this exact the category of complexes generated by just the things in the zonotope. And they showed that that thing gives a noncommutative resolution of the affine GIT quotient. And in their algorithm, they do something like this, except that they use all co-characters lambda. And so the only difference in this algorithm is that we only use co-characters that pair negatively with the GIT parameter L. And somehow this is the blend. It's the Špenko-Vandenberg algorithm, but being careful to only use co-characters that pair negatively with L that gives you something that's equivalent to the GIT quotient in the end. I hope that's clear. I mean, it was a little bit telegraphic. I didn't really explain the details, but that should give you a sense of what these categories are. So basically, if you have an orbifold GIT quotient, so if you choose an L where the GX with finite automorphisms, finite stabilizers on that semi-stable locus, then actually this D semi-stable is just the GL. D semi-stable is the entire derived category of the GIT quotient, and so you get a theorem of the kind we're talking about. And I'm applying this theorem, gives you a decomposition for any t, but basically I'm just going to apply it when t is 0 because I've introduced the shift parameter. And so basically this is what you end up with at the end of the day. If you apply the theorem, this basically was the category C0. Those two things together generate the category C0, and you get a 3-term decomposition where G psi maps fully faithfully into the derived category of the GIT quotient, and it's essentially surjective if it's an orbifold. And the thing that I like about this version of the theorem, so instead of breaking the semi-stable locus up into these strata, it somehow treats the whole semi-stable locus simultaneously, the unstable locus simultaneously. And somehow as a result of this, this G psi, which this is a convenient, this is like an indexing convention, which is kind of useful, where I think of, there's this GIT parameter, and then there's a shift parameter, and I put them both together into one complex parameter. So it lives in the Nernst-Savary group of X, tensor of C. And basically, the GIT quotient, the semi-stable locus depends on the parameter L in a kind of semi-continuous way. And now the G category also depends on the parameter theta in a semi-continuous way. And on the parameter L in a semi-continuous way. That was what was missing before, is that the G category depended on L in a kind of continuous way. And then this is what you get for that, which is that if you, let's say so what you get for that is that if you deform this parameter slightly, you could deform both the L and the shift parameter, you get an inclusion like this. So the sort of generic perturbation, so any perturbation of the parameter gives you a subcategory. And we'll see this is actually going to be the crucial thing for using this to compare different GIT quotients. First, I just wanted to make one comment, which is that, the category G was defined very indirectly. You basically take these polyhedron categories, these window categories, and you use them to find it. Semiorthogonal complement is a U minus, and then you take the semiorthogonal complement of that in this unstably supported stuff, and you get U plus, and then the G is defined to be what's between them. So it has a kind of indirect definition from that theorem, but you can also extract from this machinery, you can extract an explicit description, which is more along the spirit of a grade restriction rule. Wait, sorry, what time did I start? 15 past. Oh. Okay, yeah, that should be good. So there is a grade restriction rule basically that says that if I take E and I tensor it with the structure sheaf of the fixed locus for any of these lambda, I just want to say that the weights lie outside of some forbidden region. Okay, so I've now given you the G category. I've explained what the G category is, but now I'd like to compare this or relate this to these window categories. So if you look at just what the G category is when L is 0, so you're just getting, there's no semi-stable, the semi-stable locus is everything. It actually just is a window category. It's the category generated by highest weight representations in some shift of the zonotope. So I'll just fix theta and drop it from the notation. And basically what the theorem tells you is the semi-continuity thing that is this thing here, the semi-continuity tells you that for this window category, for any L, you get a two-term decomposition where UL is just the unstably supported stuff, and the GL is the thing that becomes equivalent to the derived category of the semi-stable locus. I should say this is when in an orbifold, when it's an okay. If it's an orbifold. So basically, there's a one category W. It's finitely generated. It has a very explicit category, and it has decompositions of this kind for every GIT quotient. And I don't know this for sure, but I think it must be the same as the Cox category in the toric case. So the Cox category is this kind of common non-commutative object that contains as a semi-orthogonal factor every toric variety that's birationally equivalent to the original one. And this would be a non-commutative generalization of that, not abelian. So I want to make okay, so that's the end of the theorems, basically. And what I would like to tell you about a little bit is like what's kind of coming next, what the expectation is for these decompositions. So to do that, I'm going to talk a little bit about this, the philosophy of this non-commutative minimal model program. So Kontsevich, Katsarkov, Pantev, Yu, they propose, some talks from Maxime from a while ago, propose these canonical semi-orthogonal decompositions. Oops, I didn't finish that sentence. So this is now in the smooth projective case that you're supposed to get a semi-orthogonal decomposition, a canonical one, up to mutation, that corresponds where the pieces correspond to the atoms of X. And then I kind of refine this by proposing a mechanism that uses stability conditions for getting these decompositions. Specifically, it's a mechanism for relating quantum cohomology to derived categories via the stability manifold. And basically, I gave a categorification of the blow-up formula. So a conjecture that there are these, so to refine this conjecture that there's a canonical mutation equivalence class of semi-orthogonal decompositions that satisfies a categorical analog of the blow-up formula. And basically what I observed is that if you believe this categorical blow-up formula, it actually implies that any variety that has a non-trivial section of the canonical bundle will have a subcategory that is a kind of minimal model in the sense that every birationally equivalent variety will also contain M as an admissible subcategory in a somewhat canonical way. And the idea is that if X is Calabi-Yau, the category is indecomposable, so it is equal to its own minimal model. And that's why you get the D-equivalence conjecture from this observation. So the non-commutative MMP was it's very speculative because it's not the stability manifold is not known to be, non-empty for most projective varieties. So it's not really something you can investigate at the moment. It's more like a dream that you might hope to figure out someday, except for surfaces, which actually people have figured it out for surfaces, which is some really interesting work. And for some examples like projective spaces and stuff like that. But basically the source of the D-equivalence conjecture, you can extract from this non-commutative MMP the following idea. So if x and x prime are Calabi-Yau, you find and birational, you find a sort of common resolution of this birational morphism. And then dB of z should have a canonical mutation equivalence class of semiorthogonal decompositions. And the categorification of the blow-up formula basically says that, one mutation, one representative in this mutation equivalence class looks like this, dB of x, and then a bunch of other stuff. And another representative looks like this, dB of x prime, and a bunch of other stuff. And so then the fact that there's this canonical one says that these are related by some mutation. And there's a little argument why that mutation actually has to take dB of x to dB of x prime. And so you get an equivalence via mutation of semiorthogonal decompositions in some larger category. That's basically what I want you to extract from this. But this is all very speculative. So the proposal here, so the proposal here is to just do this for window categories. So it's much less speculative in the case of window categories, and I'll explain why in a moment. But the proposal here is that for x mod g, back to the setting, let's say, of a linear representation of g, this window category W, the conjecture, the proposal is that it should admit a sort of canonical semiorthogonal decompositions, canonical up to mutation, and that for any L, some mutation of that canonical one refines the ones that we've just discovered. And as a consequence of that, if x mod g has this Calabi-Yau condition, then any two GIT quotients that happen to be orbifolds will be derived equivalent kind of automatically. And so my claim is that it should sort of be easier to study this. It should be easier to find this canonical semiorthogonal decomposition in this setting, and I'll explain why. So, well, the first thing to mention is that there's a little bit of evidence for this. It's a slightly different setting, but in the quasi-symmetric case, now I'll tell you what quasi-symmetric means. Quasi-symmetric just means that every fixed component also satisfies the Calabi-Yau condition. That's kind of what breaks for the general Calabi-Yau, is that you can take different co-characters and take their fixed locus, and it's no longer Calabi-Yau equivariantly. So quasi-symmetric is exactly that condition. And in that case, you can do a window category not for the full zonotope. I called that the big one. This is for this is the small window category, where it has the same description, and you just scale the zonotope down by a half. And when you do that, you have a sequence of decompositions of this kind. So if you look carefully what's happening here, so basically this window category for parameter theta decomposes as the stuff that's supported on the L unstable locus, and then a small shift of the window category. But now I can mutate. I can bring this over here, and what that actually does is gives me the window category for the shift in the other direction. And then I can do a mutation again. And what that does, this is the remarkable part, that actually shifts when I do a mutation and I bring this over to the other side, UL goes from being the category supported on the L unstable locus to the category supported on the minus L unstable locus. There's no stability condition yet. This is a combinatorial thing. Well, that's what I'll say in a minute. Yeah. I'm almost there. Well, yeah. This is just, I think it would be nice if something like this were true in the Calabi-Yau setting. I can't decide if it's true, but actually, so the point is that anytime you have a mutation, when I drag one thing over the other, I get an equivalence like this. And then I drag, and then the fact that these two things are just different incarnations of the same semiorthogonal decomposition, the semiorthogonal complement here and the semiorthogonal complement there are just automatically the G categories, because they're characterized by the stuff that's semiorthogonal to the UL. And so this is what gives you, this tracing through this mutation is what gives you the equivalence, GL equivalent to G minus L, which is exactly the proposal. And this observation for these quasi-symmetric wall crossings was earlier for the case of simple wall crossings worked out by me and Shipman. So that's basically most of the evidence. So you might ask, I showed you a very simple sequence of mutations, and I could ask if these, when I say these mutations work, what I mean is, you just do mutations on these decompositions, and maybe you can get from GL to G minus L, and maybe not. I don't know. I tried pretty hard. I worked for like a week. I can't say I'm giving up yet. It's quite possible. Yeah, you've all been there where you like put it down and then you might come back to it 3 weeks later and think you can do it again, and then you try. And anyway, so we'll see. In about a month, I'll declare it really, truly impossible, but maybe. But what that motivated me to do, and in fact, this is secretly, this question was actually the motivation for the noncommutative minimal model program for me. So I had studied semiorthogonal decompositions like this, and I was wondering, is there a more symmetric kind of semiorthogonal decompositions of the kind that I've just described to you, that I've now found with Spelle and Kimoy? But the question was, where do they come from? So you get these decompositions of the equivariant category, but where do they come from? And the noncommutative MMP was originally my attempt to answer that question. So the semiorthogonal decomposition should come from a kind of path in the stability manifold of the category that you're looking at, called quasi-convergent path. And because it's late in the talk, I'm not going to explain all the details of that, but basically the upshot is that for certain paths in the stability manifold heading towards infinity, you can pick out a semiorthogonal decomposition from that path. And so that was the original thing that made me think about that, was this equivariant setting. And then I realized that you could formulate something much more conjectural in the smooth projective variety case. So now what I'm doing is I'm returning to the kind of equivariant setting where some of these ideas were first percolated for me. So the claim is that this is a much easier setting. And the reason basically is these are algebraic. These categories are just modules over some algebra. So they already have T structures given to you. So this is the results of Špenko and Vandenberg. They've studied the same category, but from the perspective of noncommutative resolution. So they take some representation, which is the sum of all irreps in the window, and they basically define this category W as the stuff generated by that, and they take the endomorphism algebra, and so just like before, you have this subcategory of the equivariant category is actually equivalent to the category of modules over this noncommutative algebra lambda. And in cases like the compact toric variety situation, then this algebra is just Artinian, and you can classify what all of its simple modules are. And in that situation, you can just write down stability conditions. Basically, you just have to declare what the central charges of the simple objects are, and that heart with that central charge, you put them in the upper half space, will give you a stability condition. So all I'm saying is that this is an easier setting to study because we know at least some large open patch of the stability manifold is very concrete. We can study it very concretely. And now, there's a little bit, things get a little more technical. So in the Calabi-Yau case, this affine GIT quotient won't be a point, but there's other things you can do. You can work category of graded modules and things supported on the null cone, but the point is that there are ways to actually get your hands on stability conditions rather concretely. So the main question, I'm not sure I have an answer to this, but this is what I'm currently thinking about. But so a path in the stability manifold is just determined by, roughly just determined by a path in the space of central charges. That's just homomorphisms from the K theory of your category to C. You need a starting point, but once you have the starting point, you just have a certain path. So the question for what stability conditions is, the question is really what path. And you can play around with different things. It's tempting to write down a formula like this one. basically I take all the inward normal co-characters and I sum over all the weights. And what this is basically going to do is that if L pairs negatively with lambda, this thing here is always greater than or equal to 0 for mu in the zonotope. And so if L pairs negatively, this exponent has a positive coefficient. And so if tau goes to the, if tau has large real part, this x is going to get big. And so basically, I'm weighting this by the dimension of this hum. So for every destabilizing lambda, these are exactly the objects that we expect to generate the category UL. And so basically, what this means is that for this family of central charges, if you have an E in the G category, the mass goes to 0. The central charge goes to 0. And any E that's not in the G category, basically you can say what the asymptotics of the log central charge are. They go up and to the right, or maybe they converge to a non-zero value. And furthermore, if you go just straight to the right, then this thing is roughly real valued, and you just do have stability conditions out there. So the question is, if you go straight to the right and you get a stability condition, can you sort of continue this around in all possible directions of tau? And I've sort of indicated in different directions of tau for the central charge where you're supposed to get to. Here, here is where the unstably supported stuff has a large mass and the G has a small mass. If you rotate tau a little bit, you get to a region where the stuff in the G category has a large mass and the unstably supported stuff has a small mass. If you rotate a little bit more, you get the dual of the original decomposition. So the stuff in the unstably supported has a small mass, and then you get just the linear dual of this G category, which has big mass, and finally you go all the way back around. This whole family of proposed stability conditions is for the one stability parameter L. And to get the mutation that I care about, I actually want to go, there's a branch cut, and I want to go across it in the other direction. And that's the mystery that, you know, I don't know what happens if you go in the other, I don't know what happens if you go in the other direction. But it would be nice if you get this. If you could get this or whatever, then you know, if this analytically continues to the same picture for minus L, then you'd get this D-equivalence conjecture. So that's the oh yeah, thank you.